the talk is given by Dr. Samson Lasaulce. It's about communicating in the presence of goals. So I don't know what kind of goals he's going to be talking about. But Samson, I know him for many years, so I could, of course, explain his career here in the IEEE format. But basically, we were roommates more than 20 years ago, even more than 30 years ago, as students. So I know him more than enough. And then, of course, he did an outstanding PhD at Motorola Labs. And then basically he went into working for Orange for a couple of years, and then joined the most known research center in France, which is called CNRS. And since then has been working for many years in the field of information theory, game theory, wireless communication, and many others. And of course, we had also the opportunity to interact and co-supervise a couple of PhD students within 2008, 2010, when I moved to Supélec, and he was also there within a lab called I3S. And then, of course, he moved now to work in Nancy since many years. So this is why I lost track of him for a couple of years, which was bad for me. And then build up also, of course, his research career around Nancy, working also with some ex-postdoc. I think Vainit is with you?
Yes.
Yeah. And of course, has been continuing doing work on optimal control, game theory, and other aspects. So it's a real pleasure to welcome you here after all these years. And it's more like 30 years, I think. Nearly 30 years.
Less than that.
No, 25 years. 25 years. So I have good memories outside the research field with him. It was a great time. Okay. You can start.
Thank you, Meron. Okay, thank you for this very kind introduction. So I'm very happy to be here to discover this beautiful center with brilliant researchers and engineers. So in fact, I don't know exactly what you know. So I did something and you will tell me after if it is suited or not. So first of all, I have not quoted all the just need to understand. I have not quoted all the references because this is a long list. And the value of this presentation is that I did a summary of the research I did, not all the research, but some research I did, and I connected things that, papers that seem disconnected for other people. So we will see, in fact, goal-oriented communications. We have been working on that some time ago, and you will discover that. So we'll start, we'll find the complete list at the end. So in fact, the first time I realized about potential of goal-oriented communications, it was when I was teaching at École Polytechnique in Paris. I gave this paper to my students, okay? And I said, okay, look at this paper because it's interesting. You can get a compression rate, okay? A rate of 40 bits per second for speech coding, which was very low compared to the classical data rate you need. Typically, you need a few kilobits per second, say let's 10 kilobits per second. So it was much lower. So in fact, the trick behind this to compress speech, okay, the trick was very simple. The trick was that, sorry for that, was you take some speech, okay, some recording, then you convert it into text, and then you compress text. That's the idea. And then you regenerate the speech, okay, the analog part. So how do you get so low, I mean, this low value is because you convert it into text. And in fact, at the end of the day, you don't care about the identity of the speaker, you just care about the content. In fact, you get this huge improvement in terms of data rate. So it means if the goal is just to know about the content of the speech, you can decrease the rate. But now if you care about the quality, of course, and as we usually do with traditional communication systems, then you have much higher data rates, okay? So it shows that when you take the goal into account, you can really improve the situation, for instance, in terms of data compression. So of course, this example already gave it because I gave a seminar by Visio last year to TII. This is a very simple example. Well, assume you have an image, okay? And the goal is just to know if there is a ball in the image or not. So in this situation, you don't need to compress and send all the image. You just send one bit, okay? Just send one bit, and you say that, okay, there is a ball or there is no ball. So it means that from the ball detection task point of view, in fact, you can compress the image to 1 bit per image. Okay, this is the idea. So you see the data rate is really dependent on the goal. So that was the purpose of this introduction. So more generally, why should we do goal-oriented communication? Why should we adapt the amount of information you send to the goal, to the task you want to accomplish? Okay. Why should you do that? Because as you see, you can decrease the storage space. You can lower the bandwidth. You can also decrease the need in terms of computational resources. You can also increase the robustness, because if you just send the minimum information which is needed to accomplish the task, then these communications, they are less easy to be attacked. Okay, so they can be more secure. They are also more suitable to future networks. For instance, for Internet of Things, when you have objects, you just want to send the right amount of information and send it to the controller, for instance. It's also more suited to what we do now. For a long time, we have been calling about quality of service of communications. Okay, now we talk more and more about quality of experience. So meaning, what is the task that the receiver wants to do? And again, you can adapt the coding part to this experience of the user. And of course, it is useful for designing feedback channels and signaling systems. Okay, is it okay so far, at least for the introduction? Okay, now it's going to be more technical. No worries, it's going to be more equations soon. Okay, so fundamental questions you can ask is this. For a given task, okay, you have a task, can be whatever, a robot can do a task, whatever the task is, the image detection, whatever you want. What is the minimum amount of information you should send to realize the task? That's one question. Another question is that, okay, you have a given amount of information, and what is the best thing you can do in terms of the quality of the task realization? Okay, that's like a dual question. And then how to design a good goal-oriented encoder. And a good, you can use a synonym which is effective. If you, I don't know if you are familiar with the Weaver and Shannon formalization, they have been talking about 3 levels for the communication: the technical level, the semantic level, and the effectiveness level. Effectiveness level, you want, in fact, the quality of the task to be effective, to be efficient. So I'm talking about this level. Okay, so to make it simple, you can interpret what I do here as a semantic communication scenario where you pursue efficiency of the semantic communication. Okay, then you have goal-oriented communication, to make it simple. Okay, let's be more precise now. So what do I mean by a task? Now I need to be precise. So in this context, a task is in fact modeled mathematically by an optimization problem. And the optimization problem has some decision variables. Okay, you need to decide, for instance, is there a ball in the image or not? Is there this word in this sequence of words, for instance? And you have some parameters. So what we mean by a goal is that we want to solve this OP. So meaning we want to find the decision variables, which exactly the task to be accomplished. And for this, you need knowledge about these parameters. But you don't have access to the true knowledge of these parameters. You just have access to an imperfect knowledge, because in fact, these parameters is the information source you would like to know. But you just have it through coding and through possibly through a channel. Is it okay? So I recap. You have an optimization problem, classical. You want to maximize, say, a function, but you don't know the parameters perfectly. But in fact, these parameters, they have been, in fact, if you want, encoded, just like before for the image, okay? Or the text, or the speech. You have the speech here, you encode the speech, okay? And then here you have the imperfect knowledge of the speech. And for this, you need to take a decision. Is there the word, I don't know, TII in the text? Okay? It's okay for this approach? Because if you don't follow here, then it's going to be boring for the rest. Huh? So it's important to understand. So yes? Or any information you want. It can be an image, a video, or whatever you want. Is what? No, in fact, this is the source, so it can be an image, okay? And the goal here would be, for instance, this compress the image to send it to knowledge channel, and from this imperfect knowledge of this image, you need to take your decision. So let's see an example of that. Very simple example. Assume so you have an optimization. You want to maximize the function U. The function U has some decision variable called x2, and the parameters is called x0. So here in this equation, you have x0, that's the parameter of the function. You encode it into some bit, x1, and then you send it to a channel, and this information is available here to maximize this function. So you don't know the parameter, you just have access to a noisy version of the parameter. That's the idea. And the question, of course, is how should you encode? How should you encode this information so that you're not too far from the maximization, the perfect maximization of this function? Ideally, you would know x0, but you don't know it. You have an encoded version of it. Okay? And the goal is to be as close as possible to the perfect maximization. Okay, for this example? Okay, so this is some takeaway messages of the result I'm going to show you and going to be. So first, with this approach, this paradigm, you have represented what we call the data pre-processing problem. The data pre-processing problem, you know, you have, for instance, an image, you apply the Fourier transform, PWC, whatever you want, to apply things so that you have a new basis, and it's easier to quantize in this basis. Okay? That's it. So what you know, for instance, is that the parallel transform, okay, can be optimal. In fact, this is the best linear transform you can apply on data in the sense of the mean square error function. But now, when you have a general goal, okay, it's no longer the case. The KLT is no longer optimal, and this is what we have proved and illustrated. We have proved that you can find better linear transform, okay, when you have a general goal. In fact, we did it, for instance, for the LP mode. Okay, we did it, and we proved that we can beat, in fact, the KLT. Okay, and of course, you can even do better. You can use the non-linear transform. So for this, we're going to resolve two neural networks, for instance. Okay. So this is what we do. We use a very simple CNN, okay, and we went further into this direction. We really adapted the CNN to go. Okay, so maybe there's some figures here. Let's just reiterate what we learned. Yeah. It's optimal. Whatever the distribution of the. Okay, so I didn't put it, but in fact, what you need to do is this. Okay? First, you maximize this function by knowing x0. Okay? And you compare to the situation when you don't know x0. You just have an encoded version of x0. Okay? So you compare. So one time you would like to minimize the gap. Okay? And don't always have those solutions. So we need a little algorithm for that. Okay, so this is an illustration of that. So precisely this represents the relative optimality loss. Okay, how much person you lose with respect to the ideal case when you know the source perfectly. So, for instance, if you plot this against the number of iterations of a gradient type algorithm you are using to plot this, but we see that the performance of KAT there with the LP norm of the and then you see the improvement by using optimized linear. Okay. You adapt the linear transform to the goal, and what you see, typically instead of having 40% of loss, which is huge get to the maximum in 100, and you get, for instance, here from big improvement. So this is for the data procedure. So this again, these are more results that I'm going to. This is one takeaway message. You can revisit data processing problem. In fact, you know, data processing. Energy efficient resource allocation, what people did, they say, okay, let's maximize, for instance, the packet success rate divided by the power consumed by the device. Okay, for instance, this is energy efficient. And people have been working on this, on variation of that. There are many papers, many wireless papers about that. But if you think about now the goal, okay, you don't care about energy efficiency. What matters is, in fact, how you use information. It's not a packet success rate. What matters is that what you do with the information of the receiver. So you can change this approach by looking at this final goal. Then there is second notion. You can revisit resource allocation. And then this is a very interesting idea. Okay. In resource allocation problems, if you think, I don't know if you're familiar, for instance, with power control problem. Power control problem is that the device adapts power, for instance, to the channel. But here you are going to revisit this because you can use your power, okay, to encode information. And why should you encode information? Is precisely to adapt it to the goal. Okay, and this is what we did. We have revisited this resource allocation problem for a certain goal. Okay, now I'm going to be more precise about this, okay? And we are going to write some equations. So what I'm going to present here, and it is very interesting, in fact, this is a general methodology based on information theory, which allows you to know the limiting performance of goal-oriented communications, okay? You know about capacity, okay? Channel capacity. You know about all this, but this idea is to reuse this material of information theory for goal-oriented communications and to be able to maximize the performance limit in terms of goals. That's the goal. So we are going to look at this methodology, sorry. Then we are going to talk a bit about goal-oriented quantizers. So this is how you should quantize information for goal. And then we'll talk about the case of non-aligned goals, which is, I think, quite new, because typically this has been used in literature of economics. But my intuition is that it's going to be more and more popular in the case where the decision makers are devices. Okay, so that means this is quite new because the receiver has a goal, a performance metric, and the transmitter has a number one. But what I want to claim here is that for even for engineering, this makes sense. And I'm going to talk about this. Okay, so let's sum up. I think for me, this is one of the most important slides because it explains what we do. The channel communication paradigm, okay, that's a communication paradigm. So the channel communication paradigm is here. That's conventional. So for the conventional paradigm, what you do, you look at the fidelity criterion, okay? Bit error rates, symbol error rates, packet error rates, all these kind of things. Distortion, MMSE, all this kind. So that's the thing. Now we do one step. One step, we are looking at the goal. Okay, sorry. We look at the goal. So that means we're moving from this fidelity criterion to an arbitrary goal function, an arbitrary performance metric for your communication. So that's one step we do. And we are going to talk about goal-oriented communication with common goals. Transmitter, receiver has the same arbitrary goal. We'll talk about coding and one-shot. So these are two scenarios. And then the last step we'll do is that we are going to move from the case where we have one common goal to a case where we have non-aligned goals. Okay, so that's the most general case is here, in fact. And this is the most involved case. So let's look at this methodology that I have really simplified to understand how you can get the limiting performance. So I don't know if you're familiar with all of this. Tell me if you have questions. So the information source is modeled by a random process, X naught. The encoding is modeled by a sequence of functions, okay, which generates the coder outputs, which is again a sequence of random variables, mean a random process. Decoding, same story. It is a sequence of functions which generates the decisions taken by the receivers. We have a common goal function, which depends on the information source, the decision taken by the transmitter, and the decision taken by the receiver. And we did it for the case where the alphabets, the sets where these quantities are, is finite. And the goal is to average, is to evaluate the performance of the system, okay? The average performance of the system when you have a certain information. So let's look at that. If you look at the utility function, the goal, okay, which represented by this function you want to maximize, this is the coding, this is the decoding. You can always write it like that. This is the expectation, this is the average of the performance, okay, over T. T could be, for instance, the symbol index, okay? So when you write this, what you realize is that what you have at the end, you have the sum over all possible triplets. And here you have a very important quantity. In fact, you see that the limiting performance in terms of goals, in fact, depends on the average probability. What is the average probability? PT is a joint probability over X0, X1, and X2. And if you know, in fact, the feasible values for this quantity, the problem is solved. Whatever the goal, whatever the function, whatever the performance metric, it's solved. So technically, the only problem is to find this quantity. And I think this is what takes time. And you use information theory to find this quantity. But then it works for every function. Okay? So this is what we have. This quantity is the expectation with respect to P, and we call P, capital P, this quantity. Is it okay? Everyone is following? I don't know if it is trivial for you or it's, are you familiar with that? Okay. Okay, so what you see is to find the limiting performance of a goal-oriented communication amounts to maximizing the expected utility. So it means this is in fact just a linear function. So you want to maximize linear functions. The P is of course a probability. So that means it is in a unit simplex. And then you add a certain information constraint. So this is a recipe, the general recipe to find the limiting performance of a GOC. But then where does this information constraint come from? It depends precisely on the observation and information structure of your problem. But this is the only thing which changes, okay? It works for every U. That's why I'm saying this is an arbitrary goal, okay? And you just need to work to find this function. So this is the case we treated in a TIT paper. We have been looking at this time, we assume the source is IID. Before, I have not assumed it's IID. We assume this time is IID, distributed according to a certain probability distribution rho naught. assume the observation structure to be a discrete memory channel, this large, and the encoding structure we take is this. The coder at time t takes all the information about the random process, and the decoder has some noisy observation, but in a strictly causal way. That's it. And for this problem, we are able to find an information constraint. We don't need to look at the details, okay? You can find it in the paper. But here is the mutual information between the input, the decision, and here you have V, which is called an auxiliary random variable. It's just a parameter, if you want. Okay, now if you solve this problem, and you have proved, in fact, this inequality here is convex, okay? So you have a convex problem, you solve it, you will find the best performance you can do. So you give me your information you have, and then I will tell you how much you will perform in terms of U. Okay, so this is quite powerful. Okay, so we have applied this to many situations. So I just show you some performance. So for instance, I told you about coded resource allocation. Here you have an example. So assume you have, for instance, 2 transmitters, okay, and 2 receivers, and they communicate and there is interference. What is very nice here is that what we did, we have been looking at the best performance this system can have when the transmitters have SINR feedback. You're familiar with SINR, everyone, huh? Okay. What is the best performance you can have when a system, when the transmitters have SINR feedback? People have proposed algorithms, okay? You have, for instance, ITRT, water algorithm, etc. But what is the best thing you can do with the SINR knowledge? What is the best thing? So with this setup, you can do it, okay? So we did it, for instance, when you have the U is the sum rate, okay? Like a Shannon rate, if you want. When the U is the sum SINR, we did it for energy efficiency also here, okay? We did it, and we compare to the state of the art. And we have been looking at the relative gain you can make. So you see, depending on the SNR, you can get with a log SNR function, you can get as this much. When you have a linear function of the SNR, you get that much. And when you have energy efficiency, the gains are huge. So that means adapting the power control to the goal is really important, for instance, for this function. These are exponential type functions, typically. Okay? So I don't know if you get everything, but I re-explain maybe just a bit. So the idea is that you use power control, but this time you control power for the channel, which is known, which has been known for years, but you also convey information through the power levels. And why you do that? Because you exchange information through the SINR, and you coordinate with the second transmitters by using this feedback. So this is a completely new idea. It was completely new idea, but this can be, for instance, done with this type of frameworks. Everyone got the idea, I hope. Yes? So I insist. It means two systems can coordinate, two transmitters can coordinate, even if they don't exchange information directly. They exchange information indirectly through the SINR. Okay? That's the idea. And you have the performance for that. Okay, now let's move to goal-oriented quantization. So I gave a seminar on goal-oriented quantization last year, okay? So I'm not going to give you all the detail. I just want to connect the dots. So how do you get the goal-oriented quantization problem from what we saw? You get it like that. Here we had this function before, this coding function. Then it just becomes this in the case of quantization. Quantization, you have an input, and you just have one function, which is, okay? That's what's the coding part is. And for the decoding, same story. What you have these times, you just have one input for the decoder. It's a one-shot function, okay? So, and if you compose the two, sigma 2 of sigma 1, you get what we call the quantization function. Okay, so I recap. Coding, you take the quantizer input, you map it into, for instance, a label, message, and then the decoder takes this label and regenerates the input. Okay, and that you get the quantization function. So this is a special case of what we have seen so far. And you have been working on this quantization problem and how to design this time. Because before we have not been talking, here it's not about the design, okay? It's about the limiting performance. Now we are talking about the design. And this is what we do with Hangzhou, which is working with you. For instance, in this paper, you can find it. And what did we do? We have compared the ideal performance, okay? So you want to maximize this function, okay? When you know the parameters, you can take the best decision, x2 star of x naught. This is the ideal situation. But when you don't know the parameters, okay, and you just have access to a quantized version, you're going to lose in terms of utility. And the idea is to minimize the gap by choosing the best quantizer. Okay, so this is a quite general framework. So you can apply it to clustering also, because clustering and quantization, they are fully connected. The difference is that this time you have a database to quantize. You can use it for neural network abstraction or reduction, okay? This time, what would be the U? It would be like that. So this would be the function which represents your neural network, okay? So this is a decision of the neural network, okay? This is the output. This is the matrix of weights, and this is the matrix of biases, okay, of your network. And in fact, the question here you could ask is, okay, I would like to abstract, to quantize all these parameters, okay, such that I approximate my neural network for complexity reasons, for instance, okay? And how should I quantize these quantities? How should I create partition of these quantities? And this is what we do here for a simple case. Yes? So we have been looking at this problem, okay? What we did is this. We have found the best scalar GOQ, guaranteeing quantizers in the high resolution regime. We have that. We have proposed an iterative quantization algorithm for the vector case. And we did a proof of concept for data clustering case, okay, for smart grid signals. This is what we did in this paper. Okay, just an illustration. Here it's a relative optimality loss. Okay, you compare the best situation to what you can do. So if we look at the classical approach, okay, when you want to minimize the distortion, what you have is that you have this curve. So this is a relative optimality loss depending on the number of partitions of the quantizers, okay, or the number of cells if you have a clustering problem. So this is the performance you get with distortion. And this is what you get with the best state of the art. This is a paper by Yonina Eldar. And this is what we get with our approach. Okay, you really do the best thing you can do. We applied, as I said, for a smart grid performance metric. So it's smart grid, just like if you know OFDM, people have been trying to minimize the peak to average ratio. So in a smart grid system, they quite often they are trying to minimize the peak power. Okay, so that's why they want to minimize this LP norm. Okay, so when you have this function, same thing. We have applied our technique by looking at the optimality loss versus the number of clusters, okay, for clustering. And this is the performance you get here, okay? And you compare with all what you have in literatures, and we do much better again. So we really have a machinery to find the best thing we can do. Okay, let's look at the case of non-aligned goals, which is quite open. I think you can apply it to many things. So the question is, okay, you would say, okay, Mr. Lasaulce, why are you interested in this case of non-aligned goals? Again, think about you are in your place at home, okay, and you have a smart meter I don't know if you have many smart meters in the Emirates, but in France, it's very popular. You have a smart meter, okay? So the smart meter is going to give information about your power consumptions to a controller system, okay? Then why should they have non-aligned goals? Because the smart meters, in fact, what he wants to do is to give some information to the network so that the network can estimate the behavior of the network. So the goal is to minimize distortion for the network. But for you, it's not exactly about minimizing distortion, because you're okay to help the network, but you would like to have some confidentiality also about what you do in your place. So you see, you have a non-alignment of the goals. You don't want to report all what you do in your place. Okay, you want to report some information to help the network, but you don't want to reveal too much information about what you do in your place. So in this case, the two devices, the smart meter device and the receiver, which is at the controller side, in fact, they have non-aligned goals. Technically, they have non-aligned goals. So how do you design a communication system for that? So, okay, so we have been trying to look at the limiting performance of that and try to design things again. So in fact, for the limiting performance, it's not complicated at all. You just need to replace the function you had before by another function, W alpha. And what is W alpha? It is a convex combination of the goals. And if you maximize this quantity by looking at the weighted utilities, if you want, that will give you the Pareto frontier of the utility region. I mean, the best thing you can do in terms of goals for both of them. Okay, so message here is that you can extend what we did before to the case of non-aligned goals easily for the theoretical part. Okay, for the design part, it's more complicated. And let's look at that. So for the design part, things are changing. And I'm going to show you what's happening exactly. Let's look at this example. Assume this is the performance metric of the transmitter. Okay, so in this case, it minimizes distortion. You want, okay, minimize distortion because you want X2 to be close to X1. Okay, because you want to maximize it. So this is distortion. This is MMSC. This is what classical quantizers do. Now, U2, okay, this is a network. It wants to minimize distortion, but also it has another term, okay, and which is related to the cost associated to the decision X2. Okay, so this is the goal for transmitter. This is the goal for receiver. And in this case, let's look at the best quantizer. But what do you mean by best? Because what is best for one maybe is not best for two. So that's why we're looking at what we call a Nash equilibrium situation. Okay, and this is what we do. We're looking at the quantizer for the Nash equilibrium situation. And then you discover very interesting things. For instance, depending on this value B, you know, if B equals 0, the goals are aligned. If B is large, they are very different. So let's look at the influence of the value of B on the number of clusters or the number of partitions, okay, the number of parts in the partition, okay, that means the rate given by the coder, okay, depending on the value of B. If B is large, in fact, the number of parts of the partition is 1. That means if B is large, the coder sends 0 information to the decoder. And you can prove that. You can 0 information. Now, if B is smaller, you have exactly the amount of information it gives to the decoder. Okay? So we are able to formalize these kind of things. Okay, so this kind of things, you're already playing it. Okay, for instance, you want to get a job. Okay, you want to get a job and you have a value. Okay, so and then in fact, maybe you don't have the same metric as the company, because the company maybe want to minimize your salary and you want to maximize. So maybe it's non-aligned. Okay, and then you are maybe cheating about your value. Okay, to have more salary. So in fact, you can formalize this kind of things, okay? Even from a technological point of view. And this is what you see here, okay? So This is a paper when you have been looking this kind of things for quadratic functions. I'm not going to talk about this. And then you have started to generalize to the situation when you have multiple senders and one receiver. And they have non-aligned goals. So I think at this point, this thing is not popular, but maybe it will be one day. Okay, so I'm going to recap about the extension I've been mentioning in the summary, and then we'll be done. And then if you have questions, I will be very happy to answer. So we have seen how to revisit linear and nonlinear data processing, okay, in the goal-oriented communications situation. We have seen that we can use this setting to reduce a neural network. You can use it, okay? And in fact, you can even use a neural network to reduce another neural network. You can also do that, okay? You can use an NN to compute a quantizer, which will allow you to quantize the parameters. This is something you can do. We have seen that you can use this setting to learn about the communication usage of wireless devices, okay? That will give you the goals and you will adapt the coding. Because for a long time, we have been adapting the coding, okay? Modulation coding scheme to the channel. Here it's different paradigm, you adapt it to the goal. So you have both the channels, both the goal, and you need to play with that to have the best coding. What you can do also is to look at the database exchange, okay? So you have a database, okay? Fauzi has a database, I have a database, and you have non-aligned goals. Okay, I don't know. He's Falcon, I'm ChatGPT, and we exchange things, but you have non-aligned goals. Which amount of information will I give you and vice versa? So you can look at this problem like that. Data strategic communication between two NN. Okay, so two NN, we exchange information based on this. And then, as I said, when you have multiple transmitter and multiple receiver, and each device has its own goal, there is a lot of work to be done to revisit the coding part. Okay, so maybe I've been a bit fast. I hope it was clear, but thanks for your attention.
Good. So are there questions?
I would be happy to clarify things because I don't know your background. Aaron, it was a challenge for me. It's related to the IT. IT is more on an IT information theory point of view. But don't hesitate. I can clarify things or the main takeaway messages. I can.
So for us, there is big. I would say gray zone between lab definitions like semantic communication, goal-oriented communication. So how do you see things here? Because whenever you go to conference, people have different definitions of this new realm of semantics. So
okay,
how do you see? Because you have people like Emilio Spionati giving a definition. You have Venice giving another definition. So things are not clear. Then you have, of course, Shannon's Weaver level B type of definition. So,
okay, they are not unified. That's why it's difficult. So if I would like to connect the most formal works about semantics to this, okay, what I would do is this. So this is one thing, okay? I'm not saying it's everything. So one way of looking at semantics here is here. So what people who do semantics, one way of formalizing here, they put here a box, okay? And they put here what I call S, which is precisely a feature or pattern. They call it S. And then between S and X naught, there is a conditional probability, P X naught given S, okay? And this is precisely what they call the semantics. They call S. They say, okay, we're going to send this, but you are interested in S. And they want the quantizer input to be S hat. Formally, is this for many people working on semantic communication is that. Okay, so this is the first point. So how you modify it. And then the second point here, really focused on the efficiency, on the effectiveness aspect. Because for semantic people, quite often, they just look at the pattern extraction. Here, we are really focused on this given function. So that's, you can see it as an effective, you can see as a semantic communication where you have removed this and where you focus on the effectiveness aspect. You can see it like that, formally. For the rest, there are so many papers that are not formal at all. So formally, I would give you this answer.
Then the relation with source compression, because of course, semantic. I mean,
yes.
It's fundamentally source compression, no?
Yes, but in fact here, okay, I need to be more precise. In fact, this is many things. In fact, by coding, I mean in the most general sense. What do I mean? I mean this is joint source channel coding. But then a special instance of that is source coding. And this is what we do with quantization. This is a special case of source coding. So it is here. Compression is here. You compress here, okay? How should you compress such that you don't lose too much in terms of your goal? Okay, you have a drone, okay? It is very far in Dubai, as you told me, and you send compressed image, but to which extent can you degrade so that the goal, for instance, in terms of trajectory, that would be the goal, you want your drone to follow a trajectory. So to which compression rate can you go so that you're close to the trajectory? That would be exactly that. So, yeah.
So one last question is so you went into basically the more theoretical part, but then I would say the practical part is to come with, I would say, goal-oriented codes or semantic codes.
Yeah.
So are we coming up with new types of codes, or we are using the existing codes? Do you think using the existing codes, turbo codes, LDPC codes, source compression codes will be enough, or we need to invent new types of let's say, goal-oriented codes? Is there like work needed to do?
Yes, in fact, we have just started, you know, in this paper, in this TIT paper, we propose codes, okay? And in fact, we have found the best code by using exhaustive search, okay? It was possible, we have been looking at the small case, but these are completely new codes.
Okay, so you came up with a new type of...
Yeah, you can look at our paper. There are small codes. They are very small, okay? You just code, it's like final length if you want, just 2, 3, 4. It's very small code, but there are, for me, there are, why is it, I explain why it is subtle. I explain all this, I have been quite quick, I explain why it's subtle. In fact, I didn't say, but this setting, okay, is called the implicit communication setting, because you use your coder output to do two things at the same time. First, you want to convey information, but you also look at this, at the performance metric, and that's implicit communication. And explicit communication is more general than traditional communication. And to design implicit encoder, believe me, it's not trivial. We have been doing that for a simple, you know, with the SNR communication scenario. And we came up with codes I've never seen. They were very small, but they were even difficult to interpret, okay?
So it's like numeral codes. I mean, you came up with the numerical design.
Yeah, I'm saying, yeah, you have 1, 1, 0, and then you have 1, 1, 1, just exactly that, just like you do for instance, a Reed Solomon, whatever. We have been starting to do that. But I don't know about the design. I don't know if people, Mathieu Bloch told me that we could use polar codes for that and adapt, but I think he never did it, or I should check maybe. But it's completely new. And yeah.
So it means that there's an impact in terms of, I would say, product standardization by constructing new types of...
For me, what would be nice is that you create a device when you learn about all the classical goal function of the receiver. You learn the usage of, for instance, Fauzi, we learn the usage, and then you just adapt like an MCS, you just adapt to that. And you use the best codes for each task. That would be the best thing to do. Yeah.
So Wassim has a...
Yeah. Okay. Maybe it is.
Source coding and channel coding and wireless communication are usually separated. This contention, like what source community try to have the best performance, wireless community try to have the highest value. So my question is, wireless like semantic community or communication should design these two together jointly, or they
Okay, based on my knowledge, most people working there, they are talking about source compression for semantic communications. For channel, I don't know much. I don't know many contributions on revisiting the channel coding based on the semantic aspect. This is based on my knowledge. Maybe I don't know everything, of course. I don't know. Yes. Yes.
But you always say like the future will be for joint channel coding, but it's never happened. Like, maybe this is we go through like this semantic or goal oriented.
Ah, okay. This is what. Yeah. In fact, okay. The thing is that from the formalization, point of view, in fact, you need joint source channel coding. Okay. But again, you know, to do these proofs, it takes time to do this proof. In fact, I have been quick, but it takes time to prove this kind of things. Okay, here we have been looking at the most simple case where the source is IID, and when the source is IID and the observation structure is IID, this breaks typically the thing. It means that you can prove that separate a source channel coding is optimal. You see the point? Here, in fact, to do the proofs, we have been using the source channel separation theorem. And why is it working? Because of these assumptions typically. But now if you're using an MDP, for instance, an MDP process, this doesn't work and needs to be revisited. And I think you won't get the source separation theorem. And MDP is quite common. You have some state, okay, here it could be a state, and depends also on the actions. So then it becomes more complicated. And I don't know, I'm not an expert in this, but I know it needs to be revisited, for sure.
I think, I mean, the main issue with these approaches that people will tell you that you're reinventing cross-layer design with the app and going from one point to the other. What's the criticism or the answer you give to that?
What I'm saying,
people tell you, okay, now you're trying to take it from one point to the other point, from an end-to-end optimization. Okay, and that's what you're doing.
As for me, what I claim is that,
which is basically, I'm not saying simple, because of course a lot of people have been working cross-layer design, but if you want to do cross-layer design, you need to do with machine learning. You could do some end-to-end optimization.
In terms of design, I don't claim much if you look at this, but in terms of performance, okay. At least you have the notion of capacity, okay? Here you have the counterpart of that, okay? This is the counterpart of the notion of capacity for any performance metric. And this is the counterpart. Where is it? Sorry. This is the counterpart of the capacity region. I don't know if you're familiar with the capacity region of multi-user system. This is the counterpart, okay? So this is what is nice. You can really do the best. People, they propose some semantic blah, 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 but then you need to compare to something, no? And how do you do that? And for me, my knowledge is that you don't have much in literature. I have been working with Marios, you know, and Mehdi. They don't have much. So that's why I realized the work I did a few years ago, it's connected and you have the tools to do it. And that's why I've connected everything. All the works I did, huh? Yeah, and connecting dots, yeah. What? Sorry.
For example, packet loss, it's something objective, but for the goal, how can we define like objective metrics for goal? It can be something different.
Which function you can use?
Yeah.
Okay. This is what I did here. It's here. For instance, you know, the goal here. So the goal was, okay, you have a resource allocation systems, okay? And you want, okay, this one is better. You want to maximize the sum energy efficient system, okay? So the resource allocation choice is going to be used to convey information. I don't know if you got the trick before. You have two receivers, two senders and two receivers. Assume you use, I don't know, you use 4G and I use Wi-Fi. So normally two transmitters cannot communicate, okay, because they don't have the same standard. But if they both can observe their SINR, In fact, what you can do is by playing with your power, you're going to change the SINR of the second receiver. And so it gets information about what you do. So you can coordinate two systems who have not the same standards, okay, by just playing with interference. But what you do is that you encode interference. And if you encode interference, then you will do the best thing you can do in terms of coordination. So here, in this case, the goal was to maximize the sum energy efficiency of these systems, okay? And the input, okay, the X0 was the channel state. And the decision X2 was the transmitter strategy.
So I think what he's asking is, at the end, the goal is to showcase that you need less bits, doing the same thing as before.
Oh, yes,
so
of course.
It's the reduction of the number of bandwidth or bits that is needed.
Yes.
That's the metric.
Yes.
At the end, when people talk about all this framework about semantic communication, goal-oriented communication, when you look at the classical KPIs that you have in 5G and 6G, people are asking, why are you doing it? At the end, the goal is that you're saving bandwidth, saving number of bits to get the same kind of results.
But this is what this is what you say here, Miron. You have a space, okay? You have a space to be quantized, okay, for X0. If you want to get an optimality loss of 10%, okay, then with the goal oriented, you need five regions, okay? So log 2, 5 in terms of rate. And if you use a traditional approach, you need 20, 4 more. Okay, in this situation, if the rate is multiplied by 4. So you have decreased the rate by 4 for this simple scenario. Yeah, of course, this is what you mean. Either you fix the quality degradation, and then you have the improvement in terms of bits, or you do the other way. You fix the number of bits, and you have.
It's very interesting when you have perception layers, when you have different throughputs of different information. You have the reader, the radar, and you take segmentations also of the image. And you would like to transmit all these on the count of 5. So each one by itself gives you a approach. Yeah. So you mix a kind of information and you quantize. I mean, quantization also has a big role in that.
Yes.
Because this will define after the results.
Mm-hmm.
Okay.
Yeah.
So this is quite very interesting because you can compress all these, let's say, fluid gain of bits, it's huge. If I have 20 or 100 or 1 million cars, and I have to transmit between them all these perception layers together, this is mess. There is no network that will support this.
Yes.
So by default, I have to find a way to compress, to give the minimum information. The as you say, the information should be very precise. For example, this is the target, and also the compression of that. So I have to gain a kind. I have to reduce this fluent information to look on something which is kernel that express the overall information.
Yes.
And mix them. So this is quite very interesting.
Yeah.
You can get this kind of reduction of bits of information.
Yeah. For example, if you want to transmit a picture with cat, in practice, what you want to minimize is the digital range or the distortion of the image.
Yeah.
But in goal-oriented communication, we will just let the neural networks detect that it is cat. We don't care about its quality. It is good for us or not. And in this way, we will, as you presented, we train the network to minimize this picture, but all the neural network can detect that it is cat without considering its quality for the human visual systems. And with this way, we can compress perform a huge computational to preserving the quality to a human visual system.
Yes.
This is another topic in that's called machine-to-machine communication. We want to open for the machine and not for the human. Like machine.
Yeah. Okay.
This is also related to this goal-oriented
Yes.
communication. All semantic definition.
Yeah. Definitely. Yeah.
Okay, so there's a question for the person is online. And the question is, as optimizer, I have some curiosity questions about the mathematical problems you presented. What's the size of the problem you are solving? How many variables and constraints? And then how do you solve the problems? Which solver? How difficult are the optimization problems you solve? Do you solve them to optimally or heuristically? If you solve them to optimality, how long does it take to solve them? The question is you had, of course, an optimization problem on the constraints.
There were several.
Yeah, several.
There are several ones.
The question is these problems, they scale, meaning when you get a lot of constraints.
I don't know.
What kind of techniques are you using to solve that?
It doesn't work anymore. I don't know. There is a problem.
Doesn't work? Okay.
Yeah, I don't know why.
Okay, go.
The pointer is okay, but for this, it doesn't work anymore. I have no idea. But anyway, I can do it here, maybe.
No, not even. I didn't touch anything. Huh?
Really? Ah, okay. Okay, okay. So there, okay. I can,
definition of the objective function. I think roughly is just
okay.
If you're using it,
yeah.
In optimization for solving that.
Okay, there were several OPs. Okay, the first one, okay, which allows you to characterize the best performance of one receiver, which exchange information for one receiver, one transmitter and one receiver, okay, with the information constraint, okay. This problem, we have proved that the information constraint function is convex. So you have a linear function, you have linear constraints, and one convex function. So you just use a convex solver for that, okay? Now, what about the dimensionality? It's true that, okay, I have treated the discrete case because discrete case is the most general case in information theory. Then you extend it by using standard probability in spaces and you move to continuous space, okay, whatever. But anyway, so now what is the dimension of that? The dimension of the problem, optimization problem, is in fact the cardinality of x0 times cardinality x1 times cardinality of x2. Okay, so if your discrete source has, I don't know, 100, then you have 10 to the 6 as a dimension of the problem, if you have 100 everywhere.
Then we're saying, is it solvable? I mean, if you have that cardinality?
Solving convex problem with size of 10 to the 6? Yes.
The problem is always convex. Okay.
Okay. Then it depends on the information structure, but for the information structure I've shown, it's convex. Then you need to readapt to your problem. If you give me another observation structure, I have not the proof to say that every problem you will find is convex. I'm just saying that this guy is convex.
Yeah, are there questions? Yeah, no. Well, we will maybe involve to consider multiple goals. Right. To consider there's X which I can give you answers to multiple goals. And also in the time, yeah, after X which can use information X which solve the for other goals.
You're saying I'm using multiple codes?
Yes.
I don't get the question.
If you use, if, no?
Multiple codes, you mean a bank of coders? You mean, what do you mean? Multiple goals. If you use multiple goals, you mean one transmitter and then one transmitter has several goals? This is what you're saying? Yes, that's a generalization of that.
Also, y if y equals to as x, one x can use for multiple y, different goals. And with x, then we can use it to copy different y.
Yeah, but if you do that, you need to define the problem. So assume the transmitter has two goals. Okay, so what do you want to maximize there? There is nothing to. Okay, so I mean, you need to define either you use multi-objective setting, then you combine them. Okay, by using weighted sum or something like that. You need to define. Okay, otherwise I cannot say if I cannot maximize two functions at the same time. Nobody can do that. Yeah. No, that's true. I cannot. So you need to define. You need to define what you want. Okay. If you have two functions, you need to define. Once you have defined the problem, then the machinery is the same.
One thing I was thinking is, for example, I'm asking to transmit some information about you, and but because you have a relation with other people in this room, for example, maybe future I'm asking for information for other people, So maybe translating really the goal. At this time, we translate information about you is maybe not the best. For example, if you give me the relationship between this and you give me who is the most important person in this room, for example, and maybe I can input the other information about other people and everything. But maybe the first time you maybe not the specific goals of that I'm asking for you, but maybe more maybe more
for me, as I see, it's just about definition of the problem. You just need to define. What is for sure is that what makes the thing difficult is that the non-alignment thing of the transmitter and receiver, with a S if you want. Why? Because the transmitter controls one part of the coding and the receiver controls another part. That's what makes the problem difficult. But now if you're saying that a transmitter has two goals, then today you minimize or maximize that. Tomorrow you maximize another one. Or if you want to do the same thing, maximizing data rate and minimizing energy consumption, then you need to combine in some way. But it's not related to that. It's more about the definition of the optimization problem you're looking at. For me, this is the answer to the question. Yeah.
Okay, good. Are there other questions? Up here. Okay, let's thank you for the speaker.
Yeah, thank you.